Going back to our last class, we discussed some set of rules in determining the oxidation state of an element in a compound. And we talked about rule number 1, which states that the sum of oxidation state of elements in a compound is equal to 0. While rule number 2 stated that the oxidation state of an element in a free state is equal to 0. Now let's talk about the next rule that states that the oxidation state of oxygen is -2 except in peroxide. When I say peroxide, I'm talking about a reaction between oxygen and an oxide. So we have an example of a peroxide is hydrogen peroxide. So we have hydrogen peroxide. So in this case, the oxidation state of oxygen is not -2. So let's see how it is. The oxidation state of oxygen here is simply -1. So if I have, for example, plus hydrogen, where I have the oxidation state of hydrogen as +1. So if I have +1 multiplied by 2 plus bracket O2 is equal to 0. So if I have +1 multiplied by 2 will give me +2 plus O2 equal to 0. So collecting like terms, I have O2 is equal to 0. So I have here is equal to 0 minus 2. So I have O2 is equal to -2. So dividing both sides by 2 will give me oxygen as -2 divided by 2. So the oxidation state here is -1. So the oxidation state of oxygen in peroxide is -1, while in all other compounds, the oxidation state of oxygen is assigned a number -2. What about hydrogen? The oxidation state of hydrogen is +1, except in hydride. It simply means that when hydrogen combines with other elements to form a compound, the oxidation state of hydrogen in that compound or the combining capacity of hydrogen is simply +1, except in hydride. What I mean by hydride, I'm talking about elements like metals reacting with hydrogen to form a compound. Those compounds are simply called hydride. Example of hydrides are, we have sodium hydride. That is sodium metal reacting with hydrogen. It forms a sodium hydride. So in this case, the oxidation state of hydrogen is not +1. Rather, it is -1. So if I have here, the oxidation state of sodium here is simply +1 plus hydrogen to give me 0 here. So I have, collecting like terms, I have hydrogen is equal to 0 minus 1. So H is equal to -1. So in hydride, the oxidation state of hydrogen is simply -1. While in all other compounds, the oxidation state of hydrogen is assigned a number +1. Having said that, we can use this to calculate the oxidation state of an element in any compound. And we can also use this to give the IUPAC names of every compound using oxidation state or oxidation number. Having talked about that, let's go to some questions on how we can know the valency of an element or how we can identify an element based on its valency. Now we have a question here from the Jamb Utme 2017, question number 9. And the question states that 4 elements identified with the letters W, X, Y, and Z have atomic numbers 2, 6, 16, and 20 respectively. The question is, which of these elements is a metal? Of course, you can know the element whether it is a metal or a non-metal based on the position of the element in the periodic table, also based on the valency of the element. Of course, I told you that the valency of elements in group 1, which are already also called alkali metals, are given a number 1, while elements in group 2, alkaline earth metals, are given a number 2. Elements in group 3 have valency of 3, and they are also called pure metals. So based on this, we can easily identify if the element is a metal or a non-metal. So let's take a look at the question. Let's look at the first element here, which is W, with atomic number 2. So here we have 2, the first shell occupying a total of 2 electrons. So we also have element identified as letter X with atomic number 6. So here we have the first electron 2 and the next electron occupying a total of 4 electrons. So element with 4 valence electron is not a metal. It is simply carbon belonging to group 4 element. While the first case is simply element called helium, which is the second element in the periodic table with atomic number 2. Of course, we can take a look at the third one here, which is represented by letter Y, and the atomic number here is 16. So if we have this distributed in shells, we have 2, 8, 6. Okay, indicating that the last shell has a total of 6 electrons. So it requires an extra 2 electrons to complete the octet structure. This element is simply identified as oxygen with 6 electrons in the outermost shell, requesting an extra 2 electrons to make it 8. So element Y is not a metal. So let's look at the last element here, identified with letter Z. It is simply having 20 electrons with atomic number 20. Here it can be distributed as 2, 8, 8, 2. So this is clearly indicating that element Z is a metal belonging to group 2 element, which is called alkali earth metals. And alkali earth metals is found in group 2 in the periodic table, which is element calcium. So we can conclude from this question that element Z is a metal, while the rest elements are not metals. That is very simple, is it not? Now let's take a look at another question. Jamb Utme 2016, question number 9. What is the oxidation state of Cr in K2Cr2O7? Of course, Cr here represents the element called chromium. Chromium is simply a transition element. Transition elements are elements that have variable oxidation state. They also form colored ions. But we're not talking about transition elements today. Let's go back to what we have today. Now, the compound is simply K2Cr2O7, which is pronounced as potassium, oxo, dichromate 7, with the 7 written in parentheses or in Roman numerals. That is the name of the compound. How did they come about the name of this compound? You can only give the name or the IUPAC name of the compound when you have calculated the oxidation state of chromium in the compound, as it is given in this question. Now let's take a look at it. Remember, this is a compound. So we go back to our rule number 1, where we talked about set of rules assigned in determining the oxidation state of an element in a compound. The oxidation state of chromium can be calculated using that set of rules, which says that K2Cr2O7 is equal to 0. Of course, the sum of oxidation state of elements in a compound is equal to 0. So if I have potassium here, which is in group 1, the oxidation state is simply +1 multiplied by 2 plus, I make my chromium the subject of the formula. So I have Cr2 here plus -2. Of course, we said the oxidation state of oxygen is equal to -2, except in peroxide. So we have +1 multiplied by 2 will give us +2 plus Cr2 plus bracket -14 is equal to 0. So if I collect like terms, I will simply have Cr2 is equal to 0 plus 14 minus 2. So Cr2 here is equal to 14 minus 2 will give us plus 12. So we can see that Cr2 here is giving us what? Plus 12. But we are not looking for the oxidation state of CrO2. Rather, we are looking for the oxidation state of chromium, which is Cr. So we can simply divide this 12 by 2 to get our chromium. So we have CrO2 is equal to plus 12. So we can say divide both sides by 2. So I have CrO is equal to plus 12 divided by 2. CrO now would now give us plus 6. So the oxidation state of chromium in this compound is plus 6. Hence, the name of the compound is potassium heptaoxodichromate 6, with the hepta indicating 7 atoms of oxygen, while the dichromate indicating 2 atoms of chromium and the 2 atoms of potassium clearly stated there. So this is how to calculate the oxidation state of chromium in this compound. We can also use this set of rules to calculate the oxidation state of other elements in a compound when it is given in this form.